Lecture 28, we're going to continue on PIC assembly programming. We have homework 5 due today. I'll first review multi-byte data. Logical operations can be done byte by byte, and arithmetic and shift rotation instructions are required to account for data flow between bytes. For addition, we'll also consider the carry bits. If carry from lower byte, and you increment 1 in upper bytes. This is for the multi-byte counter, for example. For subtraction, we discussed the example of 16-bit counter where we have upper byte and lower byte. We're going to decrement lower byte, and if it is a 0, then we're going to borrow 1 from the upper byte. That means we're going to decrement the upper byte as well. Bit shift between bytes in shift and rotate. We'll make sure that the rotation instructions will go through the carry flag. And for rotation shift to the left, we're going to start with the least significant byte. And for the rotator shift to the right, we're going to start with the most significant byte. Again, these are for multi-byte data. We talked about subroutine. This delay subroutine will give you exactly 10 millisecond delay, and this first several instructions are used to initialize count H and count L to make up the 16-bit counter. And the next couple of instructions are to decrement and check the flag DECFSZ. These 4 instructions will essentially do the decrement lower half, and if the lower half is 0, we'll decrement the higher half. And this loop will end when both bytes reach 0. Overall, because the initial values we set in the count H and count I, overall the number of instructions executed will take exactly 10 milliseconds. Blinking LED, we use this as a more realistic example to show you how we're going to use the delay subroutine and also how we're going to check the status of certain registers and swap or toggle the bits in the same register. Here's what we did. We initialized the port D and also initialized the counter. In fact, we didn't provide you the exact code to do this kind of initialization, but we will see other examples. For the half-second delay, you can imagine that you will call the 10 millisecond subroutine 50 times. So you have a loop, and in that loop, you're going to do the call 10 milliseconds, and that subroutine for 50 times. That's how you can get 500 millisecond delay. And we talked about different ways to do the blink. Here's the typical strategy to check the individual bits. And depending on the current status, whether it's green, yellow, or red, we can determine which LED to turn on, which LED to turn off. So we'll have this subroutine, and at the beginning of the subroutine, we'll check the bit 0 of port D, because that's the bit we use to connect to green LED. If green LED is on, we will go to toggle 1, and that's where we will change the LED from green to yellow. And the way we did that is to set bit 0 of port D to be 0, that's BCF, and use BSF to set port 1 of port D to a 1. And because these zeros and ones correspond to the output voltage from these pins. If it's 0, the output voltage will be a 0 volt, and if it is a 1, the output voltage will be a 5 volt. And because the chip we use for this case is a 5 volt PIC microcontroller. There are PIC chips with 3-volt operation voltage. That will be a different story. And the output will be 3 volts in that case. And we spend some time talk about the other way to code this blink. We use a table, and this table will be accessed. Well, the value on port D will determine which return instruction that will be executed. And that return instruction will bring back 2 ones in W so that the port D will be XORed to generate the correct LED control bits. In the next couple of slides, we just briefly introduce the application of PIC microcontroller in a different scenario. In this case, we want to control a step motor. We originally had a homework 7, but it becomes an optional, so you may not need to work on that. Step motor is basically inside it has magnetic attached to a shaft, and we can control the current through those coils, and that will generate magnetic field. If we reverse the current, it will reverse the field. We have pairs of coils used to attract magnet to one of the 4 different directions. And we can have unipolar step motor where we need a central tap on the coil to make current reverse easily. So we can charge the coil, different sections of the coil, to generate current in different directions. And that way we can generate magnetic field in different polarity, then the rotor will move in a different direction. The step motor, the one we're going to use, is shown in the next slide. It's called a bipolar step motor. And the example we discuss in the next few slides are based on this type of motor. It's a bipolar stepper motor. It has more torque than unipolar step motor because the current is charged on both coils. And it is similar principle, but there's no center taps. If you look at the previous one, there's a center tap, power 1 to here. That's the center tap in this coil. In bipolar step motor, we don't have the center tap. But we do need to have some peripheral circuitry called the H-bridge, typically, to provide enough current so that we can charge both coils at the same time. So the way it works is that if you say, let's say this 1A and 1B, you see this 1A, 1B, that goes through coil here, this one, and then 1B. So you can, if you supply power between these two ends, 1A and 1B, then the current will flow either this direction or the other direction, depending on how you connect the ground and 5 volts. Okay, you can swap it or turn it off. Similarly, this 2A and 2B is another pair where you can supply current, so it will generate magnetic field. It will be able to move the rotor a little bit to get to the next position. And the idea is you alternate these directions so that the rotor, the center rotor, will move gradually, and you change the polarity again, it will move again. And you want to control the sequence so that the direction of the movement is to the same, either counterclock or clockwise. And that's all done by charging the coil or supply current in a certain pattern. And this is a table that summarizes the control sequences we can apply to those four ends. We're talking about 1A, 1B, 2A, 2B. And then you can see we have 4 bits here, 0, 0, 0, 1, and we have 0, 0, 1, 0. Each sequence has 4 bits. And these 4 bits indicate what should be the voltage supplied to that terminal. So let's say this is 1A, 1B, and 2A, 2B. That is to say, all these 3 terminals should be low voltage, and this one, 2B, this terminal should be a high voltage. So the polarity generated will be like this. So it will be like minus, minus, plus. That indicates the north, south directions of the magnetic field. So we can see that we can use different patterns to move the rotor. The first one is this: you have only one pair charged, okay, because we only have one high supply to these 4 terminals. So we only have one pair that is charged. The other pair is not charged. This is called wave drive or one phase. It consumes least power because we only have one phase. Only one phase is energized at the time, and it has. Oops. The next way to supply these patterns is to energize both pairs. So you can see in each sequence we have 2 high voltage or 5 volts, depending on the supply voltage. We have 2, both pairs were energized. This will provide you higher torque, so you have the capability to drive a larger load. This offers improved torque speed product and greater holding torque. The last way is this bottom sequence that you see. Alternately, we have 1 pair energized and 2 pairs energized and 1 pair and 2 pairs. This is called a half step. This half step effectively doubles the stepping resolution of the motor, so you can have a finer steps in each revolution. But the torque is not uniform for each step. Here's the schematic of the circuit. On the top we have the bipolar step motor, and we have 2 pairs of coils, and from there we have 4 terminals, okay? And they are color coded yellow, orange, blue, gray. And then here we have the PIC microcontroller we'll use to drive this step motor. Now in between we have this L293D. This is called H bridge. You may wonder why not just connect directly these 4 pins to the bipolar step motor, because we can program the chip so that we can generate 0, 1, 1, or whatever patterns we want to generate from these 4 pins. The problem is that, bless you. The problem is that the current coming from the PIC microcontroller is not strong enough to drive this motor. It can supply the control signals, but the current has to be supplied by the so-called H bridge, or a driver chip. So this PIC microcontroller will be programmed to generate these patterns. These control bits will be connected to this H bridge chip, which will then make sure the current will go through these coils in a certain direction. Because through the H bridge, the step motor can get enough current so that you can generate the energize the magnetic field, and will then move the rotor. This is the pattern we want to use. We're going to use the half step. So I have 8 steps. We have this up-down coil and an east-west coil. This is how we normally name them. And in the first step, we only have one of them energized, and that's this one. So it's going to generate a south facing magnetic field, while this east-west coil is off. So that's why you see it off here. In the second step, we're going to have both of energized, and they will generate this kind of magnetic field. And the third step, we're going to have this upside down, this up-down coil off, and then this east-west coil will be energized. And that translates to the control sequence. This 0, 1, 1, 1 and 0, 1, 0, 1, these are the control bits we will need coming out of the PIC microcontroller. In top row here, this RC5, RC4, RC3, RC2. This is to say that we're going to use port C of the PIC microcontroller. This RC means the port C. And specifically, we're not going to use bit 2, 3, 4, and 5 from that port. It has 8 bits, but we're going to use bit 2, 3, 4, and 5. And we're going to generate these outputs. So that is to say, we will need to configure this port C, these several pins as the output, and we're going to put these values alternatively onto these 4 bits so that we can generate this control pattern. This is what's going to happen when we generate this first sequence 0, 1, 1, 1. This 0, 1, 1, 1, because the way it's connected to this H bridge, and some of the gates will be connected. The transistors will be conducting current, and in this case, this output here will be supplying current going through this up-down coil. Well, it's color called yellow-green. So this coil will be energized, so the motor will move half step. And the other one is off. In the next sequence, 0, 1, 0, 1, then we're going to have both outputs from the H bridge chip will supply current, and both of these coils are energized, and they will move further. We're going to go through some of the code. We start with this title. Oftentimes you have this title in your program to really give a name to your program, followed by some comments. Anything you begin with semicolon, that's a comment line. Here we want to just tell the reader that what program this is for. This is a program outputs a new bipolar step motor control sequence every 250 milliseconds. And some notes on the hardware specification. We use PIC 16F684 running at 4 megahertz. And we use RC5 through RC2 for the H bridge driver control. And this list R equals DEC. This is to say that the numbers used in this program, if not specified, those are decimal numbers. And it includes this INC file. This is like a header file for C program. Now remember, we can use status, these kind of names for the registers. We can use C to represent the carry bit. Those are all defined in this header file. this underscore config, this is a little bit tricky. This is for configuring some of the features of PIC microcontroller. To give you an example, for driving the chip, many PIC microcontrollers can use internal oscillator or external oscillator. Even for internal oscillator case, you may choose to run the processor at different frequency, 16 megahertz or 64 megahertz or 8 megahertz. And those features are controlled by specific control pins, control bits. Inside the PIC microcontroller, there's a small amount of memory called the configuration memory. With lines like this, you will set bits in that memory so that the PIC microcontroller will know, okay, here I'm going to use my internal oscillator runs at 4 megahertz. Probably I will turn off my watchdog timer feature for this program. So there are a lot of things you can control from the hardware level, and you're going to use these configuration bits to do that. These are not what we talk about PIC assembly language instructions. Okay? This is just specific to the controlling the features, operations of the PIC chip. It's not the program. It's not the user program that we designed. Okay, now we're gonna declare two variables. It's called delay, and then the other variable is called I. Delay is gonna be stored at address 20, and I is gonna be at 21 hexadecimal. Okay, ignore the page. ORG0. Okay. ORG is for origin 0. This is to say, the next line, which is typically an instruction, this instruction will be put at address 0 in program memory. I hope you remember that we have program memory and data memory for PIC microcontrollers. In program memory, we have two special locations: reset vector and interrupt vector. Reset vector is 0. Or when you power on the chip, when you reset the chip, whatever instruction stored at address 0 will be executed. So if we have this ORG0, this NOP instruction will be put at address 0. That is to say, when you power on the chip, the first instruction to be executed is this NOP. ORG's origin? Yeah. Next few instructions are used to select the functions of the port and also clear the content of the port. Let's see, move LW1 with a 2 less than sign and 2. That is to shift 1 to the left for 2 bits. So essentially we're putting a number into W. Okay, this is 1 shifted by 2 bits. To the left, 2 bits. So that's this value will be put into W. Then we'll do move. This value will be put into port C. Right? Then we're gonna put 7 into W. So that is 0, 0, 0, 0, 0, 1, 1, 1. That's 7. Then we have this pound 0. We're going to put the same number into this CM, COM. You're gonna see a lot of these gibberish kind of names. These are the configuration registers for the PIC. I just want to explain this example. I don't want to go over every single one because it's very much PIC dependent, PIC specific. This CM count 0, this is to put this value into this register CM CON 0. This is the comparator configuration control register. Why we're doing this? This is the PIC, and we have RC5, RC4, RC3, RC2. These are the 4 bits we use to control, to generate the control patterns, the sequences. Remember, when we talk about the controllers, especially for PIC, many of its pins are multiplexed. So these RC pins, they are also used for comparators. So in different application scenario, you may use these pins to compare the voltage between 2 signals. What we want to do here is, we want to say, we're not going to use these pins for comparators, because we want to use these pins for IOs. We want to output those control sequences. And the way we tell the microcontroller is by setting proper values in the corresponding control registers. And this CM CON 0 is the control register for the comparator functionality. This 1111 will just turn that off, turn that functionality off. The next 2 instructions are to select bank 1, and we're going to do this ANSEL. This is again ANSEL. We're going to put the value in it. Actually, we're going to put 0 into this register to say that, hey, these pins, I want it to be analog. I want it to be digital. Because you could use these pins as analog signals. But what we want to do here is digital. It's either 0 volt or 5 volt. That's digital. For analog, you're talking about could be from 0 to 5 volts in the whole range. But for our control sequence, we just want it to be either 0 volt or 5 volts. Okay? So that's the purpose of this instruction. Next instruction, move LW, this binary sequence, and we put this try SC. Okay, look at what we put in. We're putting 0, 0, 0, 0, 1, 1. That's this instruction here. First, we'll put this value into the working register, and then we move the value from the working register to this try C. This is to make sure that this is a 7-bit value, because we're talking about the within the bank. All right, this try-SC, tri-state and C. If I mark these bit positions, just didn't write down. This corresponds to these 4 bits, corresponds to these 4 pins. This ANSEL will make these as digital pins. But digital pins, you could still be an input or an output. Okay? Even for digital, you could be using the pin as a digital input or a digital output. Do we want input or do we want output? We want output, right? We want those 4 pins to be output pins. This try SC, this is the control register to say, out of the 8 pins from port C, which pins are inputs and which pins are outputs. If you have zeros on that particular bit location, that pin will be output. If you have a 1, that pin will be input. It's easy to remember because O is output, 1 is input. So with this instruction, we can put this 0, 0, 0, 0 onto bit 2, 3, 4, 5. That will make sure that these 4 pins are now digital output pins. Yeah. We don't really care because if we're not using them, we can put either value. Just happen to be 1, 1. And now you get to the dirty details of PIC programming. It's different from x86, right? Because you now have the capability to deal with individual pins, and there are a lot of functions you can do with those pins. And you do need to set the proper values in the control registers and configure the pins properly. So we just talked about the nitty-gritty details that we need to take care of at the beginning to set up proper port control to make sure that we use those pins as digital outputs. And then here's the main loop. At the very beginning, we set high, low to this delay variable. This first instruction, move literal W, is to put a number into working register. And that number is generated like this. It'll first divide this 250 millisecond, and this is in a unit of microsecond, divided by 5, then plus the 256. This high is to take the higher byte of that 16-bit number. This number, this calculation within the parentheses, this is the number that's a 16-bit wide. So we're going to take the high byte and put that into delay. And we're going to take the lower byte, just put it into the working register. Then what we do here is to just add LW minus 1 is really do the decrementation. We're going to decrement 1 from the lower half of the counter, of the initial value. And we'll check if the result is 0. If it is a 0, we're going to decrement the delay, which is the higher half. And then we're going to also check whether the higher half is 0 or not. If it is 0, we're going to skip. Otherwise, we're going to go back to here. This $sign minus 3, this is really to say that we're going to go back by 3 instructions. So that's to here. Okay, of course, you can have a label to say that. I want to go back to the label. But this is just another way to do it. Then we'll copy the value W into I. Copy the value of I into the working register W. Then we're going to call switch read. So that's switch read. Here you see this add WF PCL comma F. Looks familiar, right? This is to add the value of W into PCL for the purpose of jumping several instructions further. Then you see this DT and DT. Okay, this DT here, this is really the table. This DT is followed by 4 binary numbers. The compiler, the assembler, will really generate those RETLW instructions using those bits. So you can think about this line is the same as having 4 RETLW instructions, and with these individual values as the operands. Then this second DT. When you have 6 bits, then that means the upper 2 bits are really zeros that you don't really care. You don't have to write down those upper 2 bits. So you now have 8 RETLW instructions. So this switch read, this subroutine, functions similarly to the blink table subroutine. So depending on the input, which is in W, it will take different return values and return to the main program. And that's returned from here. When the subroutine returns, it has the proper return value put into the W already. So this move WF will put that return value into port C. So this is really to, depending on what you have currently on the control sequence, you're going to generate next control sequence, and by using this table. And after that, we will do this counter I. Counter I will be incremented by 1, and it will clear the bit 3, which is to really just use the lower 3 bits. Then we're going to go to back to the loop. This is to make sure that this I, the value of I, will change from 0 to 7. Once we have that, so when you call the switch read, the W will be either 0 or 1 or 2 up to 7. So these bit sequences will be used as the control sequence. Do you follow me? Not exactly? Okay. Let me go back to here. This part is for the delay. Okay? We have a high byte, low byte, and we do decrement so that we'll have some kind of delay. And then we copy the value of I into W. This I is basically to say for the 8 half steps, which step I'm at right now. So the value of I will be copied into W, and then we call this switch read. We get to here, and depending on the value, the step number could be from 0 to 7. We will get one of these 8-bit sequence, and one of these 8-bit sequence will be put into W and return the subroutine return back to here. At this point, W has the proper control sequence. So that control sequence will be copied to this port C. And port C is the port we use to control the H bridge. So that's how we send out the control bits out. Then we increment this I to move on to the next half step. Right? We have 8 steps, or 8 half steps. This increment and then BCF I, 3 is to make sure the bit 3 is a 0, so you won't go over 7. And then we go back to the beginning, to the delay, then get another control sequence, and then move on. So the end result is that you have some amount of delay, 250 millisecond, you send out a control sequence, and you move on to the next step, and do that over and over. Okay?